Alright, here we go. 6.4, States of Matter and Changes of State. So we saw a bit of this in the gizmo, the idea that there's energy involved in actually changing state as well as just heating or cooling something. We have a few different changes of state, and you might have seen these words before or you might not have. That's okay. We're just going to talk about them. So the first term here is fusion. It's another word for melting. And this is when we go from a solid to a liquid. And vaporization is when we go from a liquid to a gas. Okay, so that's gaining energy. We're heating it up from solid to liquid to gas. The next row here we have condensation. This is where we go from a gas back down to a liquid. And freezing, where we go from a liquid down to a solid. Okay, those are our four terms for changing states, and those we'll be using a bit. The last one over here is called sublimation, and this is where we go from a solid to a gas, or a gas back to a solid. So either direction we call it sublimation. It's a bit confusing because it's the same word for both situations. But it's a strange situation because it means that we're skipping over liquid entirely. We go straight from a solid to a gas, or straight from a gas to a solid. It's not very common. There's not a lot of stuff that does it. So this is where it skips over liquid. And I've been using L for liquid, G for gas, S for solid. Hopefully that hasn't been confusing. So it's not common. There are some situations where it happens. For instance, dry ice goes straight from solid to gas, and so you might have seen pictures of dry ice, this solid that sort of smokes, and it's super duper cold. Anyway, we don't see it a whole lot. Those are our changes of state. And the next thing we have here are some pictures of what's happening during a state change. And we have, at the top, we have pictures of the state. So you can see the furthest left picture, it looks like solid. And then you can see the next picture to the right, we have a bit of solid floating in what looks like a pool of liquid. Okay, and so that's where we're changing. For instance, if we have ice here, you know ice floats in water. So that's a bit of ice at the top floating in water. And then you can see the next picture, it's all liquid, and you can see that because the particles are moving around more. The next picture, we have liquid at the bottom and gas at the top. And the last one is all gas. Okay, and on the right we have the reverse process, gas all the way down to solid. So that's our situation. And again, we saw a bit of this in the gizmo, but what happens here is as we're warming up the ice, well, we need to put energy into it. So this is a graph of the thermal energy absorbed as the temperature increases. So, or rather, it's as we put in more thermal energy, it's what is the temperature. So you can see that here, as we put in more energy, the temperature goes up a bit. Over this period, we keep on putting in more and more and more thermal energy, and the temperature doesn't change at all, because all that energy is going into heating up that, into changing the state from solid to liquid. Okay, then we have another region here where we're heating it up, and that's going straight into temperature. That's all we're doing, we're just increasing its temperature. And then we have another period here where the temperature doesn't change and we're just changing state again. So we pump in more energy and it's just to change the state. And then at the end here, again, we have temperature increasing once it's at a gas. So that's what this looks like. And I guess the important idea here is that temperature isn't the only thing that changes when we put in energy. We can also change the state. And at the top here, I'm going to say that thermal energy is equal to potential energy plus kinetic energy. And we said that temperature is average thermal energy. So this is, average kinetic energy. So this is average EK on the right here. And you'll see that there are certain regions where our thermal energy is not increasing the kinetic energy, like this region. And that's where we're increasing instead the potential energy. We are increasing the potential energy. And that's because our different states of matter have different amounts of potential energy. Liquid has more potential energy than solid does, and gas has more than liquid. And that's just, there's potential energy in terms of how the particles, how the molecules interact with each other. And so that's where all this extra energy is going. It's going into the potential energy of changing states. Okay, and on the right here we have again the backwards situation. You can see that this is thermal energy being released now, and we're releasing a bunch of energy here to change states down to a liquid, and we're releasing a bunch of energy again down here to change states from liquid back into a solid. And so once we're in a solid, we're at the sort of lowest potential energy that we can. It's really easy for things to be solid. But they need a lot of extra energy to become liquid, and even more to become gas. All right. So that's what this looks like, these graphs. It would be useful if you know how to interpret these graphs. When you see one, you should be able to look at this straight line and say, oh, I know what's happening. It's changing state. Okay, that's important. All right, so moving on, we have an idea called latent heat. And latent heat is the total thermal energy to change states. Okay, I'm going to say the total here. I'm going to underline that word again. So it means that if I have 100 kilograms of ice and I want to melt it, then the total thermal energy to change that whole 100 kilograms, that's called my latent heat. Now, specific latent heat, well, all we've added is the word specific, and specific means we're just looking at a single unit, for so 1 kilogram of it, that sort of thing. So specific latent heat is the energy to change 1 kilogram of a substance from one state to another. And it's just like our specific heat capacity, where that was to change 1 kilogram by 1 degree Celsius. So when we see this word specific, it generally means that we're dealing with a single, like a certain amount of it. We're only looking at 1 kilogram and 1 degree Celsius instead of looking at the total. All right, and so it means that each substance has its own specific latent heat for different processes. Now remember, we have two processes basically. We have going from solid to liquid, and we call going from solid to liquid, we call that fusion. So then we have a specific latent heat of fusion for each different material. So it says, how much energy does it take to change the state of 1 kilogram of aluminum, or 1 kilogram of ethyl alcohol? How much energy does it take to melt 1 kilogram? That's what these values are, the specific latent heat. Okay, and so we have going from solid to liquid, that's fusion, and we have going from liquid to gas, that's vaporization. And so again, we have a different set of values for the same materials for changing that state. And you'll see that they have different numbers. It's not the same going from solid to liquid as it is liquid to gas. So aluminum, we have, it takes 6.6 times 10 to the 5 joules for each kilogram to melt it. And that happens, this is another useful piece of information here, the melting point. It tells us at what temperature does that happen. Aluminum, you can see it's a very high temperature. Alcohol, well, you know alcohol is normally liquid, so it melts at a fairly low temperature. But we can make solid alcohol if we freeze it, if we get it really, really low temperature. Carbon dioxide, same thing, except carbon dioxide is normally a gas. So you can see that the boiling point is up here at negative 57. So we already know that most of the time carbon dioxide is a gas. And water, of course, we have boiling melting points of 0 and 100. That's what we define our Celsius scale based on. Alright, so this table comes in a lot of handy when we're doing any sort of calculation for how much energy is being used to boil or melt something. And it goes the other way around as well. So if I'm going from liquid back down to a solid, it's the same thing. It's this latent heat of fusion that we're going to be looking at. Because you'll see in our graphs up here, it took the same amount of energy going forwards as it does going backwards. So the amount of energy gained to change that state is the same as the amount lost to go back. Alright, turn to the next page, and we've got here a little summary here. The latent heat during a change of state, during melting and freezing, well, remember latent heat is the total energy, and we call it Q, because that's our amount of heat energy. It's equal to the mass times the latent heat of fusion, so LF, latent heat of fusion. And that was in our table on the previous page. And for boiling and condensing, we have Q is equal to the mass times the latent heat of vaporization. Good. So we can actually do some math with this now, which is always a good thing. The first problem says how much thermal energy is released by 652 grams of molten lead when it changes into a solid. All right. Well, first thing off, we need to get the latent heat of fusion for lead. We pop back onto the previous page, go down, and lead, you can see latent heat of fusion 2.5 times 10 to the 4 joules per kilogram. So we can say 2.5 times 10 to the 4 joules per kilogram. That's our latent heat of fusion, and we have our mass is 0.652 kilograms. Q is equal to mLF, which is 0.652 times 2.5 times 10 to the 4. And that gives us 16.2 kilojoules. That's how we do this sort of calculation. So that's how much thermal energy is released. And it is important to keep track of, are we gaining heat? Are we losing heat? So here, we're taking liquid down into a solid. Solid has less energy. So we're letting go of a bunch of that energy. It actually heats up the surrounding area. All the air around it is going to be heated up because the lead itself is losing that heat. Okay, next one here. Ethyl alcohol is a liquid at room temperature. How much thermal energy is absorbed when 135 grams of ethyl alcohol at 21.5 Celsius is heated until all of it boils and turns into vapor? Okay, so this is interesting. We've got ethyl alcohol at this temperature. That's not its boiling point. So to start off with, we need to heat it up until it gets to its boiling point. So there's going to be two stages here. The first stage, we're going from 21.5 degrees Celsius, and we're heating it up until it gets to its boiling point. We'll check that on the previous page. Ethyl alcohol boils at 78.3 degrees Celsius. So we go 78.3 degrees Celsius. This is our first step, step 1. And I'll put a little colon here. Well, this is what we learned yesterday on the previous lesson. So this is Q equals mc delta T. We're changing temperatures here. And we need the specific heat capacity for ethyl alcohol. And so this is where a formula sheet is definitely going to come in handy. I am not going to look it up right now. I'm just going to use the number that I have here. It's 2.46 times 10 to the 3 joules per kilogram degree Celsius. Okay, that's our C, so we can say Q is equal to our mass, 0.135 kilograms, times C, 2.46 times 10 to the 3, and times our delta T, so the final temperature minus the initial, 21.5. That gives us 18,000 863 joules. That's step 1. So again, this is how much thermal energy it takes to heat it up that much. Step 2, now we're going to go from a liquid up to a gas. So this is our step 2, and for this we have Q is equal to mLV. And we look up the LV for this substance. It's on the previous page. Ethyl alcohol, 1.1 times, don't look at the latent heat of fusion, which is what I just started to do. Look over at the vaporization. You need to use the right state. So 8.6 times 10 to the 5. 8.6 times 10 to the 5, and that's joules per kilogram. Okay, so we've got Q equals mLV. So the mass, 0.135, and our latent heat of vaporization. That gives us a Q of 116,100 joules. And notice that's way more energy than it took to heat it up. And that's usually going to be the case. Changing state takes a lot of energy. So then we do the combined, because we just need to add those two together. So we have Q1 plus Q2. This is 18,863 plus 116,100 gives us 135 kilojoules. And that's our final answer. So there we go. That's the idea here. You'll have a few problems where you do that. There's one last topic here that I want to talk about first, which is water. Water, a special liquid. Well, yes, it's very special. So water, compared to most solids, water is, sorry, hang on a second here. Water is more dense than most liquids. And so water is more dense than most liquids. There's a reason for that. It's because of the molecular shape. Now, solid water, which we call ice, of course, ice is less dense than liquid water. And this is really uncommon. Almost always, the solid of a certain substance will be denser than the liquid. So that if you have solid and liquid mixed together, the solid will sink and the liquid will float. And we know that for ice and water, that's not true. So in this case, the water sinks, the liquid water sinks, and the solid floats. If you have ice cubes in your water, they float up to the top. And that's very uncommon. That is not what most solids will do. Now, that is a very important thing. It governs a lot of how the world works. You know that if you go out to the lake, or if you go to a pond or something like that and it's winter, then the top layer will be ice, and then we can go and we can skate on it. It also means that all the fish can still survive underneath. That's because the ice is less dense. If it wasn't, all the ice would sink. The lakes, the oceans, things would be very, very different, and the world just wouldn't work the way it does currently, just in terms of how life operates, if this property wasn't true. Okay, so it's pretty cool. Now, it is because of the molecular shape of water, because water has this neat sort of, well, sometimes looks like Mickey Mouse, but it has this neat shape where we have our two hydrogens and our oxygen. And so that's an interesting thing for the liquids, but especially for the solids. What happens is they will form together because each of our oxygens then has these two sort of hydrogens sticking out, and it ends up connecting to the next oxygen, and to the next one, and to the next one, and they form these little hexagonal shapes, which is not very dense, right? There's a lot of empty space in that shape, and so this is ice, and it's not dense. You see there's a lot of empty space, which is why it floats. Okay, that's the lesson. That's what we're dealing with changes of state. Enjoy the homework.